Let's say I have the molecule sodium chloride. We know in this situation, let's look at the periodic table. Sodium, it's an alkali metal. It has one valence electron. It's in group 1. And so when it only has one, it really wants to give it away. And chloride, or chlorine is a halogen. And it's only one away. It just needs one electron to have full 8 valence electrons in its outermost shell. So it really wants to take one electron. And we've talked about this story multiple times, especially early in the chemistry playlist. And we know what's going to happen. Sodium, since it wants to lose an electron, it's going to lose its electron. And it's going to give it to chlorine. And chlorine is going to gain it. And so you're going to have a situation where sodium is going to have a +1 charge, because it lost an electron. And then chlorine will have a -1 charge because it gained an electron. And then they'll be attracted to each other because this one is now a positive atom and that one's now a negative atom. And just the Coulomb force will make them want to be with each other. And we call this, of course, an ionic bond. I haven't taught you anything you don't know yet. In an ionic bond, you literally had a loss of electron from one compound to another. Now, that's a very cut and dry situation. But we saw other situations where it wasn't quite as cut and dry. For example, H2O, where you have a oxygen, but you've seen this multiple times already if you're watching this playlist in order. And it's bonded to 2 hydrogens. But we know that oxygen is much, much more. In fact, nitrogen, oxygen, and fluorine are the most electronegative atoms, which means that they like to hog electrons the most. So when you have oxygen bonded with pretty much anything, but in particular in this case, hydrogen, it's going to pull most of the electrons in its direction. So even though these are covalent bonds, the hydrogen is still sharing the electrons that it's bonded with oxygen. Most of the electrons spend most of their time on the oxygen side of this whole affair. So you have a partial negative charge on the oxygen end of the molecule, and you have partial positive charges on the hydrogen. And we talked about this, and this is what leads to hydrogen bonding and all of that. What we're going to do here is introduce, it's almost an intellectual tool. We know that this isn't an ionic bond. We know that this is actually a covalent bond, that this atom is shared. But it spends most of its time at the more electronegative atom. That's why you have this partial negative charge. So we create this convention called oxidation states. Let me write that down. And I'll clarify what the word means in a second. Oxidation states. Oxidation state. And this is essentially assigning, with an ionic compound, you naturally assign a charge because each atom really does have a charge. But let's say we want to live in a world where we don't like this partial charge, partial negative. We want to say, look, if this were, hypothetically, if this were a ionic bond, what would it look like? Who would gain the electron and who would lose the electron? So in the case of water, if you were forced to say, OK, who gained the electron, you'd say oxygen gained 2 electrons from the hydrogens, and the hydrogens lost each 1 electron to the oxygen. So the hydrogen would have a +1 charge, each of them, and then the oxygen would have a -2 charge. Now, I want to be very clear with this. This isn't what really happened. This is just our little intellectual game that we're playing called an oxidation state. It's going to be really useful later to understand why some reactions occur. But I just want to be very clear. This is a hypothetical charge if these were ionic bonds. So you're just saying whoever is the more electronegative, and remember, electronegativity, it goes from the bottom left to the top right. So these are the most electronegative atoms, which means they love to hog electrons the most. These are the least, or you could also call them the most electropositive, which means they like to give away electrons the most. So what you do is you say, OK, the more electronegative, let's just say that they actually get the electrons, and that the more electropositive atoms, they give the electrons, even though we know that it's something in between. It's actually partial. Now these numbers, these hypothetical ionization, well, I guess we could call it hypothetical ionization of these hydrogen molecules, this is called their oxidation number. Oxidation number. The oxidation number of hydrogen in H2O, so in H2O, the oxidation number of hydrogen is +1. So we could write a +1 for each of the hydrogens there, and then the oxidation number for the oxygen is -2. -2. And the way we talk about it, we say that the hydrogen molecules here have been oxidized. And it's kind of like saying that, you've been, well, in this case, they were oxidized by oxygen. And this is actually a very confusing point, or at least it was to me initially. Because when I first learned about oxidation, I was like, oh, that's what oxygen does to things, because the word has the word, it has the word oxygen, or at least the beginning part of oxygen. So I thought, oh, oxidation must mean what oxygen does to other atoms, which means it takes electrons away from them. Usually it takes 2 electrons for itself. Maybe it took 1 from each of the other atoms. So if you've been oxidized, you've had electrons taken away from you, and so you'll have a positive charge. Now that interpretation is only partially true. The reality is it does not have to be oxygen that's doing the oxidation. So for example, let me do hydrogen fluoride. Hydrogen fluoride, HF. I've shed my habit of writing fluorine as FL. I've now remembered that its elemental symbol is just F. So hydrogen fluoride, if it was in an aqueous solution, it would be hydrofluoric acid. That's hydrogen here bonding with fluorine, one of the most electronegative atoms. So what's going to happen here? Once again, the reality is that hydrogen is sharing, it's a covalent bond with fluorine, but the electron spends most of its time here on the fluorine atom. So you're going to have a partial negative charge here and a partial positive. But we don't like this partial halfway game. We want to say, look, if this was, hypothetically, if this was an ionic bond, if one of these people had to gain or lose an electron, how would it play out? In that situation, this guy likes to hog electrons more than hydrogen does. So the fluorine would gain an electron and have an oxidation number of -1, and the hydrogen would lose an electron and have an oxidation number of +1. In this case, hydrogen has been oxidized. 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 And notice, there's no oxygen to be seen. So the way I think about it, fluorine did to hydrogen what oxygen would have done. For example, if I say that you've been Bernie Madoffed, Bernie Madoff might not be the actual individual who's taking your money and putting it into a Ponzi scheme, but it would mean that someone else is doing the same thing that Bernie Madoff would have done to you. So in the same way, even though there's no oxygen here, fluorine has oxidized the hydrogen. Now I'll introduce another word, and that's reduction. Reduction. It's the opposite of oxidation. I'll write it in blue. Reduction. And this just means a loss of a reduction of charge. So reduction of charge. So in this hydrogen fluorine molecule, or hydrogen fluoride molecule, hydrogen has been oxidized. It's been oxidized because electrons have been taken away from it. That's what oxygen would have done to it. And so it has now a positive charge. And its oxidation number is +1, because it's exactly 1 electron would have been taken away from this in a hypothetical ionic bond. Now, fluorine has been reduced. Reduced. Its oxidation number, its oxidation state, was reduced by 1. It now has, it went from being, if there was no hydrogen around, it would have been neutral. But now it has a -1 charge, because in our hypothetical world of, there's no partial charge, it's more electronegative. It took the atom from the hydrogen, so it has a -1 charge. Its charge has been reduced. Its oxidation state has been reduced. Your oxidation state is just that hypothetical charge. And that's how I think of it. Reduction means reduction in your hypothetical charge. Oxidation means what would have oxygen have done to you, which means it would have taken away electrons, which would mean you have a positive charge. But if you look in some textbooks or some teachers, they'll give you a mnemonic. Leo says grr. Leo the lion says grr. I'll say says in small because it's really irrelevant to the mnemonic. Leo the lion says grr. Grr. And this is just a way of remembering that, okay, Leo, like that means losing electrons is equal to oxidation, and that gaining electrons is equal to reduction. Now, to me, when you first said, wait, I'm gaining electrons, but I'm getting reduced. What's getting reduced? What's getting reduced is your charge, because electrons are negative. You're gaining something with a negative charge, so that's where the reduction comes from. Oxygen comes from the fact that oxygen will normally make you lose electrons. It will normally take electrons away from you, even though oxygen might not have anything to do with the reaction. Now, there's a couple of, we can look at the periodic table and we can guess in most molecules what an oxidation state of a given atom will be. All of these guys are alkali earth metals, and this is really a review. I mean, it's kind of taught as something new, but we know all of these guys, they love to give up electrons because that makes them stable, because they have this one electron in their outer shell. So they tend to have an oxidation state of +1, which means that they tend to give away an electron. For example, if I write sodium chloride, in this case, the oxidation state is truly reflective of their charge. It gave away. Its charge is equal to its oxidation state. It gave away an electron. And that's true for all of the alkali metals right here. Remember, I don't include hydrogen there, because hydrogen is a little bit of a special case. It could have been thrown here on the periodic table, because it has one electron in its outermost shell, which is just its only shell, but it's also happy to get two and have a configuration like helium. So you can almost view it as it's very close to completing its shell. So it sometimes has alkali metal type properties, and sometimes it has halogen properties where it wants to gain electrons. So hydrogen, let's say hydrogen is bonding with one of these guys, right? So let's say you had lithium hydride. Lithium hydride. So in this case, lithium, it's right here, it loves to lose its electron. So it'll lose its electron. So it'll have an oxidation state of +1. And it'll lose its electron to hydrogen, because hydrogen is more electronegative than lithium. So, because hydrogen, you give it one electron, then it has an electron configuration like helium. So hydrogen will be -1. In this situation, when hydrogen bonds with people roughly on the left-hand side of the periodic table. So lithium, just to review our terminology, lithium was oxidized by the hydrogen. Hydrogen was reduced by the lithium. Reduced. Its charge went down. Their oxidation number, +1 for the lithium, -1 for the hydrogen. What is the total sum of an oxidation state for a neutral molecule? In this case, you add up the charges, and you get, it's equal to 0. And that's a big takeaway. That in general, if you have a molecule, if you have a neutral molecule, let me write that down. If you have a, if you have a neutral molecule, I'll just say neutral compound. Neutral compound. Then the oxidation states add to 0. And if you have a non-neutral compound, if you have a +1 charge, the oxidation states of all of the molecules in your compound are going to add up to your charge. So for example, if I have, let me give another example. So in this case, I had hydrogen bonding with these guys. In that case, hydrogen is the one that took the electron. But if, let's say, I had OH minus, so OH, H minus, OH minus. So hydrogen in this case, when it's dealing with something that's not on the left-hand side, when it's dealing with a super electronegative atom, hydrogen's oxidation state is +1, right? So hydrogen is +1, +1. Now, oxygen's typical oxidation state, when it bonds with almost everything else, and I'll give a special case in a few moments, is -2, because it normally takes 2 electrons from other things. We saw that with the water. Oxygen's oxidation state, in most cases, is -2. So even though it hasn't gained 2 electrons here, we would write its oxidation number as -2 for the oxygen. And then you add up the 2 oxidation numbers, the 2 oxidation states, -2 plus 1. And then you get, well, actually, I'll take that back. Oxygen has gained an extra electron because this is already an ion. So in this case, this OH, oxygen has stolen an electron from someone else. Let me draw that. So it's OH. And then oxygen normally only has 1, 2, 3, 4. So oxygen has completed its valence shell. So it's essentially, it took an extra electron from someplace else. So it definitely does have a -2 charge in this case. Oxygen has a -2 charge. Hydrogen has a +1 charge because this electron was taken from it by the oxygen. And so the total charge of this molecule is -2 plus 1, which is -1. And that's why you have a -1 charge on OH. So you add up the oxidation states, and you're going to get the charge of the atom under question. Now, we already saw that most of these guys have an oxidation state of +1. These guys here, the alkaline earth metals, have an oxidation state of +2 because they like to give away 2 atoms. We already saw hydrogen, if they bond with people here, they take the electrons, so they get reduced. So it has an oxidation state of -1. But if hydrogen bonds with these guys on the right-hand side, it gives away the electrons. So it would have an oxidation state of +1. We saw that with hydrogen fluoride. It would be the case with hydrogen chloride, hydrogen bromide. You saw the case with water. All of these cases, hydrogen is the one that's giving away the electron. So it gets oxidized. And these guys get reduced, or they're the oxidizing agent. Now, what about these guys over here? What about our halogens? Well, they all like to take electrons. So their typical oxidation state is -1. Oxygen's typical oxidation state, we just saw, is -2. And I'll show you an example, which is really one of the few cases where oxygen doesn't have a -2 oxidation state. And then there's a lot of these other elements in between can have multiple different oxidation states, and we'll see that in a lot of examples. But if you know that hydrogen is plus or -1, if hydrogen is bonding with these guys, it's a +1, it gives away electrons. If it bonds with these guys, it's a -1, it takes the electrons. If you know oxygen tends to take 2 electrons, so it has a -2 oxidation state, and the halogens take 1. If you know that, you can normally figure out all of the other people in the compound. So what I'll do is I'll leave you there for now. I realize I'm running over time. In the next video, we're going to do some maybe more difficult examples.